It, the title is Canonical delooping machine. Actually, this will be one example actually for my future work, like research. So my work, I'm interested in like deformation theory and model light theory actually, and also a little bit about mirror symmetry actually. So this one is, for this one, like the reference is this Bernard Bazio and Alexander Boromov. And joint work with these people and John. So that is Canonical delooping machine. Journal of Pure and Applied Algebra. In 2007 to 40. So let me first notation first. So this topological top substar means this is the category. Here objects are pointed spaces, topological spaces, and then morphisms. Morphisms are pointed map. So here, typically for this one, like X star, this one maps. This is just the home, like X to Y based maps. So then here, like this category has like actually finite limit and core limit. Especially this one has like the difference between this pointed space and just the spaces is the like kernel, like the null. We can define kernel by using what the null object. Here we have the null object actually. Null object is the initial and what terminal object, which is the base point. But when you have like topological space, so then we have like point space would be what? Just terminal object, but this is not initial object, right? The initial object would be what? Empty. But in here, like this point object would be what? Initial and at the same time, what? Terminal object. That's the difference. So this category, actually, this category has in the home functor, in the homes. This means you have the home functor. You have this home functor, and then this is again what this means. This is again topological space, right? And then and also this one has the joint, left joint, which is the product function, right? Then for this one, like the question is like So this, we have in the home functor, so then this is again a space. So then how can you recognize this kind of like mapping space? So this would be different from a general like space, right? How can you recognize? So the question is, how can we recognize such a mapping space?
So the question is, in other words, this functor is going to be a representable functor, but we don't actually know how to construct this representative functor in terms of topological space. So you want to construct that space in terms of certain concrete space. Is that what you were trying to do?
Actually, we will move to like homotopy category. So up to homotopy, we want to recognize this one. By like this will have some special like properties, right? This will have some kind of like algebraic structure. This would be different from general space. Those would have some kind of algebraic structure. We are going to use those algebraic structures, and then if some space has that kind of algebraic structure, then we can say those kind of space would be like up to homotopy, like those are what mapping space.
So it doesn't have something to do with the representability of the.
There is like on the homotopy level. So on the we moved. So we take like, we consider the homotopy category with this one, and then in there still is this representable in some sense. Yeah. Mapping space up to homotopy, actually up to wiki equivalence. The intuitive idea is the following. So this is like some kind of space, and then in general, like in algebraic geometry or in algebraic topology, how can you recognize like those kind of spaces, spatial spaces? Usually, like as Grösendik mentioned, like what's the general space? General space would be functors from that category to set, or in this case we have in the home functor. Then those would be functors from the category topological space to the topological space. So that's how we can recognize those. Like we can describe those like objects. So intuitive idea, what I'm saying is natural. Describe such mapping. As certain functor from, of course, if I use the whole topological space as kind of testing category, then we can describe like each object. But this one has something special, so we are not going to use the whole category here, like certain category, certain actually subcategory. Playing space. This kind of idea is like very natural actually. Like in moduli, how can you like if you have this is some kind of moduli space. Let's say this is moduli. Some moduli space of some structures. Let's say you can think about associative algebra structure or some complex structures, etc. Then, for example, how can we want to know the at one point you want to know the germ, for example. How can I set up that kind of? How can I compare those like local deformations, right? For that, like for this kind of problem, the one you can say this certain category is kind of testing category. You know what I'm saying? For this one, the testing category would be alternate local. This would be the testing category. So you can think about like functors from these two sets in this case. Considering those, like we can recognize the germs of this kind of moduli space.
So for the topological category, can you use as point CW complexity, for instance, as a testing category? Maybe it's too small?
That's, yes, that's almost the same as what. If you take the homotopy category, then those would be the same. So that would be too much. And then here, basically, then what is certain subcategory? So this, how can you choose this one? For example, in this case, we are going to use kind of algebraic one, algebraic operations. So for example, how can you, like in, for example, like the category vector space. So then here, in vector space, some object are what? Algebras, right? So here, like algebras, A is, let's say A is algebra, right? That means A is, of course, if you forget about the algebra structure, then that is what? Just a vector space, right? So how can you recognize those algebras, for example? To do that, like, we can only consider the like finite operations. You can think about A tensor A to A. You can only consider, if this object is algebra, so then here, like, we have like spatial, universal, like operations there. You know what I'm saying? Those are the multiplication, right? All those algebras will have what? Those multiplication, and what? They will satisfy like associativity, things like that. You know what I'm saying? For the kind of algebraic one, so what I'm saying is we can only use like this kind of A tensor N to A, this kind of maps, like finite operations. Actually, for this one, we are trying to do the same thing, actually. And then eventually we'll show, so we'll show the homotopy category of, so we'll describe this kind of mapping space as just a functor, certain functors, right? So that category, so this would be the category of, first of such mapping, those mapping spaces, right? Mapping spaces. And then the other one is the homotopy category, the category of such functors. And then we want to show that actually these are what? Equivalents. That's what we want to do. The homotopy categories are equivalent. This says like, this says the title actually. Just think about it. If you have some, this means like if you have some y tilde here, right? We have certain functor. So then this must be what, some kind of mapping space. So we go here, and then this will come back, right? So then those would be what? Those would be, actually this map would be taking the loop, like nothing but the taking the maps, like some x to this one. So this one would be some mapping space x to b, y tilde, something like this. We'll get this kind of isomorphism. So that means like this, that's why this is called the delooping. This space would be, if you, those are delooping, but you can say demapping, right? If you demap this one, we can find the target space. So that, how can you show this equivalence of these homotopy categories, right? So that's question. So this kind of things, like nowadays, like in like mirror symmetry or like moduli space, what we do is always what? Comparing those homotopy categories. Homotopy category, this actually really means like localization. It's not just the homotopy category marked by like interval. You know what I'm saying?
Could you explain more about homotopy category? What is homotopy?
Yeah, I will explain those later, but those are like localization. Here, like we have some weak equivalence, let's say, some morphisms, right? And then we are going to call those, we are inverting those morphisms. like for example, you had like something we have like originally mapped x to y, right? But this is isomorphism on the cohomology level. But can you find then the inverse here, really? We don't have those kind of things, right, in this category. So localization means we are inverting this kind of, we are giving like imaginary like maps here.
Question about the morphisms by defining these things to be isomorphism. You can, the objects are same, but morphisms are going to be quotiented out by those.
Yeah, it's not really quotient, but yeah, so yeah, look, that's a there is like here. Then you may ask then here this what is this one? This is like you can think of it. This is like this cohomology is functional from topological space to you can say graded like let's say just vector space even or whatever some graded let's say G modules, right? So then we localize this one. We localize this one in one sense. So if here, as I said, this is localization, right? This is how we localize. Then we localize, we get homotopy category with this one. And then we have graded Z modules, right? So then next question is, can you say these are isomorphism? These, what I'm saying, the homotopy category, these are isomorphism. This is not isomorphism, actually. That's why, like, so far, like, mathematical invariants are like cohomology or like global shifts or whatever, global sections or whatever it is. Like those are what we had like category, and then we got some better understood like category, right? And then we localize those. That means we can say like if the image of this one is isomorphism, then let's localize those morphisms. So then can you say those categories are the same? If those are categories same, we don't have to actually study this homotopy category. Those are different. And then those are different. So that's why instead of studying this one, if we study this one, then we lose. In other words, if we study cohomology, homology, then we lose too many informations. But in here, like we still have this homotopy category or localization, this still have more information, a lot more information than this one.
Probably I don't understand the meaning of localization of the category. What's localization?
Localization just if you have a ring, right? Then if you have a ring, then this is like some multiply closed set here. So then we can localize this one, right? We are inverting those things, right? It's the same thing. You can think of a category with like one object. This is morphism. All itself, you can think this is like a category with one object, only one object, right? And then morphisms only, let's say star. Then here, morphisms are just what the R itself. And then here now, localization means we originally had some in the ring. So in here, like M is in here, right? So then those originally doesn't have like inverse, right? May not have an inverse. Now, the localization ring means we are inverting those kind of elements, right? We do the same thing for the category. So in here, like in localization, the morphisms are, you can imagine like the real map. And then the second is this like F, this is S. Then this S is from the like weak equivalences. Things like this one. Or you can think like, you can say like here, you can say like just like group. Why you can think like that? Because actually the morphisms are some kind of algebraic structure. Actually, composition is algebraic structure on the morphism. Actually, when you have like morphism between groups, right? We are modding by the kernel, right? That means here, like if you goes two objects goes the same, right? So then what you do is we identify those two things, right? Here we are doing the same thing. We don't have like zero object, but what you're going to do is like if those two morphisms, you can say, give isomorphism, then we are identifying those morphisms.
Artificially inverting certain particular class of morphisms, such as homotopy equivalence, so that we can actually have a controlled morphisms in the quotient category.
So yeah, so you can think like to compare two categories. Like here, let's say this is like full. Full means here all more selective. So then we are modding this one. Like if those two morphisms goes the same, then we are going to identify those things by giving inverse map. Originally those we don't have an inverse, then we cannot say those two objects are the same. That's what this said actually. Yeah, so what I'm saying, so most of the problems people are working on nowadays are like comparing the homotopy categories, like localization of categories. Typical example is what the homotopy category formal deformation problems. These are the homotopy category is same as the homotopy category of differential graded Lie algebra. And then this is actually same as formal pointed differential graded manifolds. Those are the main like thing in deformating theory nowadays. Actually here like we can do almost the same thing, like deformated theory, as I said, what we are trying to understand the germ of moduli space. Deformation means like, in moduli space we have one structure means we have one point, right? Structure means we have one point. And then we want to know the deformation means the neighborhood of this one, the germ. To do that, as I said, we are using the testing category, this one, alternate algebra. We can set up the problem like that. Those are deformation problems. So then, those problems, and then differential graded Lie algebra, this is some kind of better than this one, right? And then this is almost same as you can say differential graded co-algebra actually. But anyway, so those, if you look at the homotopy category, then those are the same. So that's why like usually people says like some deformation problem is controlled by some differential graded Lie algebra, then in that sense. Yeah, so then how can you show that? The idea is first like we have to get such a functor, right? I didn't define such a functor yet, but we have to define, we need to get such a functor. And then the second step would be like, usually like we want to show the equivalence of categories, right? So then of course we will not have equivalence on the direct category. We are localizing something, we are modding, right? We are identifying something on the domain category. So that means, but still we need to have adjoint, at least adjoint functor. Adjoint is weaker than equivalence. So we can get actually, it's left adjoint functor. And then the third one would be, and then we get like adjoint functors between those two categories. We can say maybe just adjoint functors. So, and then after we get like functors between two categories, right? We comparing these two categories. without the homotopy category. And then we got first, like we get adjoint functors here. And then we are localizing both categories. And then we are comparing those two categories. Both categories. Then check if those are equivalent. That's what we do in general, actually, to show the equivalence to homotopy categories. So this part nowadays it's called, this would be homotopy theory, actually. This part is called homotopy theory nowadays. So then first, like how to get like such a functor, right? As I mentioned, we had a mapping space. We want to recognize this kind of space, right? So to recognize this kind of space, algebraically, as I said, consider all natural, actually here, finite type operations. On mapping space. So this means we are considering like all maps on this one. This is A space, right? This is in the category of topological space. And then we are considering all natural operation on that object. So here, like as product, as I did like before, like A, this is algebraic object, we consider like maps from this one, right? But in here, like this is kind of operator version, so we only consider like one output operation. But in general, we have to consider several outputs too. So here then, this should be plus M. So then this, what is this one? This is nothing but, we have co-product actually. Co-product means the wedge of this one to X. And this is maps from wedge M, A to X. Right, this is not, this, you have like wedge means like we have a bunch of A's, right? These are A's, and then we have maps. So each one gives us one map, right? Product. So then actually this says, as you can see easily, like if you have maps, just consider this one, maps from M's wedge over A, N's wedge over A. If we have some map here, F here, then this will give us like F pullback. This is just what? G goes to what? G circle, composing F, right? So we have this kind of natural. This means any element in here will give us what? Natural operations on here, right? This is nothing but the Yoneda lemma, actually. Yoneda lemma says this is maps from M to A is just isomorphic to natural transformation between those functors. You can forget about X. So then this is maps from which N A, this functor to the home functor. So, and then that is actually, these will give us, this means these will give us all natural operations on mapping space, right? So we can describe those as like functor, actually. We can think of these are objects, and morphisms are these kind of things. And then we have like functor from this category to what? Topological space. This actually says TA, let's say TA is the category. Here, objects are just wedges of A. And then morphisms are this one. Morphism TA, like to wedge M to A. So then this is maps from wedge M, A, to N, A. We switch those two, right? And then this, what is this one? This is just isomorphic to maps. If you use coproductness of this one, then this is same as A, wedge N, A plus M. So this category has these object morphisms like this one, and then this means this is coproduct again, and then if I take the dual, so we switch those two, right, in this. So that means we are getting product now. This is originally coproduct, right? And then product. So this is a category with product, right? This is just a, so that means this would be like product of n copies of A in this category, right? And then that category, and then I'm trying to describe functor, which give us what the mapping space. So here, this means, so now if its mapping space, let's say A to X, this will give us a functor such functor like from the category TA to the category topological space. Yeah, the functor would be like if you have here object are these, right? So then this just goes to maps and to A to X. So each mapping space gives us this kind of functor. Mapping space, and then we are going to get the inverse actually, right? Homotopy inverse. Those are actually product of resolving functor because of this one. So this was product in this category, right? This becomes product here. So this kind of product of resolving functor. So call such functor, such product preserving functor let's say TA algebras. So then, so what I have done is the following, like. Now you can think about the category with T, this kind of product preserving functors, right? We are considering all that kind of functors. So then this is TA algebra. And then let's say TA algebra, this is the category all TA algebras, all such product preserving functors. Then what we just did is the following. We just constructed a functor from topological space to TA algebra. So here, this was just what? If you have x, then this is omega of ax is defined by this one. This is functor, so project space. So if you have A here, then this goes to maps from let's say A to X. And then our goal is, so we describe it like mapping space. So if you have this, if you have mapping space, then we have this kind of like TA algebra. So we globally, like we got this kind of functors, right? So we are going to compare these two categories now. So our goal is getting the homotopy inverse. That means we are taking homotopy category, we localize both, and then those should be what equivalent. That's what we want to do. Now, as I said, that's the first. So we finally constructed such a functors, right, which describes a mapping space. And then now what we have to do is now we have to find the lefty way adjoint functor, right, to compare these two categories. So the second is left adjoint. We want to find the left adjoint functor. So then this one, the idea is like, this is just, you can think this is like, TA looks complicated, but this is just the functors from what? This category, TA to topological space, right? This is subcategory of this one, actually. The difference is here, we require.
What is A?
A is just general space.
Topological space?
Yeah, topological space. Yeah, pointed.
So for each point in space, we have just associated a functor that sends to send the object to the TA.
So you have from topological category, you have TA algebra category.
Yeah. At what? Just one level, like you can. This is just a. Without these wedges, right? This just means just to construct the mapping space, the target space, like X. So here, like, how can you find? You can just imagine this is what this is just. You can imagine like easily like what this is just kind of mapping. Just taking maps from what A to X, right? That kind of functor. So then, as you know, what do we have? What do you have is we have a home functor actually, as I mentioned. What basically this is what A to. This functor is adjoint to what? These two adjoint. The functor, this one, right? Like algebraic, like the what? The home functor. Like when you have like A, then the dual functor, the adjoint functor is tensor functor, right? The same way. So we just extend this to like as functors.
Is A cross really the cross or the?
Here actually wedge, if you like, all of these are like too simple for actually what that's based map. So yeah, it should be wedge.
Wedge.
Yeah.
Modulo this.
The based point part. So actually, like, this is X, this is Y. So then there is base point, right? These are base point for X, this is base point for Y. Then we are modding all these parts.
There's a smash point.
Yeah, smash point. Yeah, yeah.
Not wedge.
He called it
Oh, sorry. Yeah, wedge. Wedge. Yeah, wedge is the other one. Sorry. Yes, wedge should be one like this. Right. This is X. This is Y. Yeah, sorry.
X cross Y.
Smash. Yes, smash. Yes. Yeah.
But
Yeah.
in latex, the backslash wedge gives us this.
Yeah, but we can find it by using this one. Actually, we can construct this left joint function for this one. Like, let's say in general, like if you have C opposite, we have two functors. No, if you have just these functors, right? So then what's the this will give us like what this gives is this will give us like functors from the project space to what the project space to C. Actually, we don't need that. So this functor would be like as we did just by using the home functor. So here, if you have x, so then this is nothing but maps from f, and then this one. This is C to project space, right? So we can the joint functor is the following. So what you need is like we need to construct this kind of functors, right? We need to construct this kind of functors, which is your joint, left joint. So here, if you have some G, right? So then this will goes to F tensor G over C, where this F tensor G over C, this is an equation to co-equalize this is where CD F C morphism T to C. This looks probably complicated, but this the co-equalizer of this one. This here like J1 is mapped from FC. J1 is this FC GD. So this we can evaluate this one, right? This is you can evaluation map just to, so then evaluation, then just identity on this one, and then wedge all of those. So then similarly J2 is defined. This would be J1, and then we take the co-equalizer. This looks complicated, but this is generalization of like tensor actually. If you start with this is nothing new actually. R is the category. this is a ring as category. Right? So this is ring as a category, then just one object and morphisms are itself. And then if you have functors are opposite to like what? The category abelian. Here this should be, let's say this is abelian groups, right? So then this is, whenever you have functors, this will give us well left like modules. Or like if you have R to abelian, then right modules, you know what I'm saying, by using the composition. So then actually this tensor, you can describe this tensor by using this general tensor. We get this one. The tensor would be what? Exactly this one actually. That's what I did in the middle. Like what I had is this. Let's call this is what? Modules. This is modules, right? Left, right modules. So then this co-equalize just means what? I say is M tensor. There is only one morphism, right? So the middle one is R, and then N, right? And then we here like M tensor N. So this first one means like multiplying this one, right? So we get this one. And then second one, this is J1 and J2. And then we get the co-equalize. The co-equalize, so this one exactly the what? Module M tensor N over R. But anyway, so what we have is so what I have is the following. So originally we had a functor. This two T algebras, right? The character T algebras. And then what we construct is this is left joint, right? Let's call. I use the general C, but in this case, let's say BA. BA is just like this one. Here, T algebra. So if you have some functor here, right? So those functors, what? F is functors. This is TA to such a functor, right? And then we can. This goes to what? F tensor G over T A. Actually, I should use this. This. So if this kind of functors, then we tensored with F. Right. Nice. What is this F? Oh. Yeah, F is the functor coming from the A, right? This functor f. Right. What they use? Right. This means in the A, we always goes like this one, right? So that kind of functor. That's what I mean. Yeah. So finally we get to like orthojoint functors, right? We are comparing those two categories. Now, what the next step would be, we localize both categories, and then we are going to compare those categories, right? And then third step is localization. Then the question is then how can you localize this one? First of all, think about this here. This is like this is like it's not like what 1-to-1. So if you have something here, we got mapping space. Just easy, like if you have x, then you can think if you forget the higher terms, then there is just the maps from what x to this kind of functor, right? Sorry, this omega a, then this should be a to x, right? This kind of functors. Now what I'm saying is, now here x, y, maybe it goes to what same elements, right? Because typically, like what? For example, if a is Sm, so then this one Sm, let's say Sm, and then even like star Sn and just a point, then obviously this is just a point, right? And then here, if m is what? M is greater than n, right? No, S2 the other way. S2 to S3 we have maps, Hoff maps, right? So then what I'm saying is this is still point, right? This is point 2. But we started with like SM and star. These are, it's not homotopic, right? Those goes to what? Same object, right? So we have to identify those two. You know, those parts of localization. So we are going to call those what? Isomorphic, right? In the homotopic categories. That's how we localize that category. So on here, project space. So f x to y, this is weak equivalence. If and only if maps star x to a to x, so we have this map, right? A to y, those are what weak equivalence. So we are modeling like this kind of this space, this category, right? So then we localize with respect to this one, and then how about this category? This category on the category with T algebras. On here, the localization is just point-wisely. So this is a functors, right? So what I'm saying is x tilde and y tilde is weak equivalence. So then this just means at each value, each point, this is a functor from wedge AN, right? Those are y tilde and a, those are weak equivalence. Point-wisely, you can just point-wise, those are weak equivalence. We localize this category like that, and then we localize this in this way.
Sorry, when you When you say weak equivalence here, what does that mean? Does it mean?
In this case, right? So this case, like topological, yeah. Actually, here, like we use a different like localization. Originally, we have to use that too. Originally, I should like use some like this one. In here, like weak equivalence. Originally, this means XY is weak equivalence. This just means the homotopy groups are isomorphism. Originally, right? But in this case, we cannot use that directly, right? Because as I said, what this here, two different like object goes the same one, right? So we have to identify those things. We localize this category in that way.
So in case A is replaced by P as the we actually recover the original one, but actually here we are using something much more general.
Yeah. Yeah. So it's like here, this kind of actually we can get this one if n is 0 actually. N is 0, that means like S0 is just consist of 2 points. Okay, those are actually just the space itself. Like what I'm saying is map from S0 to like X. This is nothing but the X itself. So in that case, we get actually this one. It's the same thing. Okay. Yeah, we localize in both categories, and now, so we got the T algebras like this, like chain complex, both are, right? So in that case, originally, if this original functor is like exact functors, right? Exact functors, then kernel and co-kernel would be preserved. In that case, then on the homotopy category, you'll get directly the derived functors. If you have left exact functors, then you will get only like left derived functors. Right exact functors, then you will get only right exact functors. Things like actually, those are big tools. Like probably I should mention like to study those homotopy categories, localization. The main like known tools are like so-called model category. And also another one is when you study the abelian categories, so then you know a lot more things about this homotopy category. You know, so if you study the abelian category, in this case, like you study the abelian category, then you'll consider like chain complex, and then right chain complexes, and then you'll consider the homotopy category of this one, localize the quasi-isomorphisms, right? That's how we actually get the triangular category, which is needed in mean symmetry.
So model category is a kind of generalization that we actually use that kind of homotopy category for the abelian category. Is it what you were saying here? So for abelian categories, we have a standard procedure of obtaining the homotopy category, the complex category, derived category, and the model category is a kind of generalization for arbitrary categories.
Yeah, for arbitrary category, but the problem is like here, like if you study abelian category, the homotopy category, we are not looking at this homotopy error, it's just a category. We are looking at this one as triangular category. So we have some extra structures on the homotopy categories, right? That's the point. But in here, like if you start just model categories, then the derived category is just the category itself usually. You know what I'm saying? But this is like in general case, like general this is for general categories.
Is this model category same as what some people say equivalent category?
Yeah, equivalent category. It's the same.
I never studied this.
Yeah, actually, abelian category is also actually model category. We can give the model category structure, but But when you look at this aberrant in this way, that means we are looking at one more structure, the triangular category structures, right? And that's how, like, when you study the coherent shifts, right? Then that's how we compare, like, two, like, what schemes, especially like Calabi-Yau, like that. We can mirror symmetry. But anyway, so this. Yeah, and then I want to say, so we have actually the derived category. This functor was what? This, so is the A, right? And then this is, we will have right derived functor here, omega A. Okay, and then it turns out these are order joint. So it says like on homotopy categories now we got the order joint, right? And then now now are these equivalents, right? That's the next question. And then if in general this is not equivalent. So far for general space I used like A, right? General space A, right? To describe a mapping space. This kind of mapping space, right? If I start with general A, then we can get equivalence here. But still we can get a joint here, okay? But if A is like general Sn, and it's greater n spheres, so then what I can say is those are equivalent. Okay, but in general, it's not true. For example, like if I use like here A, if A is like S2, wedge is S3, then it is false.
What property of Sn makes this one?
This Sn is like this. This is probably this is like co-product, like homotopy this is homotopy co-product, right? You know what I'm saying? The homotopy co-product. That's right. So then we have like Sn to X. This will give us what? Always the homotopy class, right? This will give us group structures, right? This has that kind of group structure. So this Sn is Sn is actually what? In the category topological space, that's an actual homotopy group. That's why it is possible. That's why we are only, and also this is why this is not true. It's because actually we only used like finite operations, right? As when I get the original functors, right? What I use the only like finite operation. That's why, because, and also like this is true because this one has like, how can you describe it like groups, right? For that we only need like a finite operation. Yeah. It probably has stop.
I feel like I've been walking in the sky.